Alright, this video is the start of section 3 of the chapter and probably the most difficult section in this chapter. The other two sections were probably mostly a review for most of you. But section 3 does deal with gas behavior, and this is kind of an abstract topic because a lot of times we can't really, can't really see gases. So you kind of have to look at models or simulations of them. And one of our labs is going to look at simulations of gases. But before we get into all of that, we need to look at how we measure gases. So how do we actually view gases? Because we can't really see them. So we got to see them in three different measurements is what we do. One measurement is volume, one is temperature, and the last is pressure. Volume and temperature should be pretty familiar with you. Pressure might be a little abstract, so pay extra close attention to this video, and if you have to watch it a couple times, then make sure you do so. Our first one we're going to look at is volume. So just as a reminder, volume is the amount of space an object takes up. It is measured in milliliters or cubic centimeters, depending if you're a solid or a gas. So keep in mind we're probably going to be doing milliliters here because we're a gas right now. Keep in mind that gases do not have a definite volume. So they're going to fill whatever space you allow them to fill. So it's going to be whatever container you put them in, that's the volume of the gas. So the volume of the container is going to be the same as the volume of the gas. So if I take my container and I crunch it up and make the volume smaller, then the volume of the gas gets smaller. If I blow my container up and inflate it some, then the volume of the gas increases. So it depends on the container. Next is temperature. Recall, temperature is an average. Right? Thermal energy is the total amount of particle movement. Temperature is the average amount of particle movement. So at a high temperature, think we are moving faster. So that's one way to tell how much thermal energy we have is the higher temperature you are, the faster those particles are going to move. Think of a thermometer as a speedometer, right? As you increase your speed, the faster you go. So the faster you go, the more speed you have. The more your particles are moving, the faster they are moving, the more temperature they have. Our last one, I'm over here. I'm going to go up in this corner. Well, there we go. Our last one is pressure. Pressure is collisions. That's what I want you to think of it as. It is collisions. If you are moving fast, then you tend to collide into things more. Whether that is the outside of a container or another particle, the faster you move, the more collisions you're going to have. So keep that in mind. That's one way that temperature and pressure are going to be related. But these pressure comes from this constant movement of these gas particles. Remember, gas particles already have a lot of thermal energy, and therefore they're going to be pushing against the sides of their container, wanting to expand it, and you're just not letting it because you're controlling the volume of the container. Again, when you increase the volume of the container, you're going to increase the volume of the gas because they want to push it out. Pressure is measured in pascals. We're not going to get too much into it, but it is pascals. One way you can remember that is our little corny joke here we have. If you know who Sir Isaac Newton is, that's our picture here. This is Sir Isaac Newton. Newton measures forces. Pascal is the whole thing here. Area is a square meter. So here I got a meter by a meter. That's our square meter here. So our joke is that what is it? It's Galileo, Newton, and Pascal are playing hide and seek, and Galileo's he's counting off, going to 100, while Newton runs off. And no one finds him really. He just runs away. While Pascal, I'm sorry, I'm ruining the joke here. Yeah, Pascal is the one that runs off, and nobody finds him. Newton, on the other hand, he stays where he is, and he just draws a square meter around him, and therefore, when Galileo is done, he opens his eyes, sees Newton right there, and he's like, well, I found you, Newton. He's like, no, I'm a Newton standing on a square meter. I'm a force over an area. You found a Pascal. So Newton's little joke there. Keep that in mind. Pressure is collisions. That's what's important right now with pressure. Pressure is also going to help you determine a lot with sports because of inflations of balls. So if you can think, if I have a container that has a flexible volume, such as a basketball, I can deflate a basketball and make it have a small volume, or I can inflate it and make it have a large volume. You have a higher pressure when it's inflated, and therefore it's going to bounce better because all those collisions are going to be happening, and when you collide with the floor, it's going to push it back up. That's Newton's third law of motion, which we'll get into when we start talking about physics. But the higher the pressure inside the ball, that's what's going to keep it inflated. Excuse me. If you overinflate your ball, then it bounces very well if it doesn't pop. If you underinflate your ball, it does not bounce very well at all and is probably easier to pass around with. So keep that in mind. There is also pressure happening outside the ball because there's a gas outside that ball as well. So everything is going to be relative to the pressure outside the ball. So if I increase the pressure, make the pressure inside the ball higher than the pressure outside the ball, then it bounces a lot better than if I have the pressure lowered.